I am Nitishas and welcome to the section of Grade 9 CBSE Maths class. Today we are looking at the chapter number 10, circles. You all know what is a circle and how will we draw a circle. But in this chapter, we are not discussing about the construction of a circle, or we are not discussing about how to draw a circle. But in this chapter, we will discuss the theorems related to circles and how we will prove that theorem based on the problems we have in our board exam. Clear? So as a basic thing, we have to mention or we have to explain what is a circle. Basically, what is a circle? Just think yourself in your mind, what do you mean by a circle? A circle can be called as a collection of infinite number of points. A circle can be called as a collection of infinite number of points. Now a doubt arises in your mind that if we are taking the points like this, that means in a straight line, then how these points together be a circle? So in addition to that collection of points, we have to add some more to give a meaningful definition of circles. So I am adding that a circle can be called as infinite collection of points which are at fixed distance from a fixed point. Now, if we take a fixed point and looking at these points are not at fixed distance from this point. As the point like goes on the right side or left side, the distance increases. Now it gives a meaningful idea. Now it makes sense that a circle is a collection of points from a fixed point and at a fixed distance. Now consider a fixed point. This is our fixed point and taken as A. And I am taking a collection of large number of points which are at a fixed distance from this fixed point. I can take only the points which are at the same distance from this same point. So I am taking this distance as x and marking a point. Now I can take only the points which are at a distance x from this point O. So I am taking another point which is also at a distance x. I am taking another point which is also at a distance x. I am taking some more points which are at the same distance x, which are at the same distance x. Now these all are our points. These all are our points. We can select infinite number of points like this. We can select infinite number of points like this. So when these points are connected together, we got a circle. When these points are connected together, we got a circle. Now we can explain what a circle is. We need to have a fixed point and it is a collection of large number of points which are at a fixed distance from a fixed point. That is a circle. Now I am considering a circle. Like that. This is our circle. This is our circle and this is the fixed point as the center. Now when we check the distance from this point to every point on a circle, it should be the same. It must be the same. When taking all distances from this fixed point towards the point on the circle, then all these distance should be the same. If all these distance should be the same, then this circle, then this collection of points can be called as a circle. Then the collection of points can be called as a circle. Clear? Now you can define a circle as circle is a collection of large number of points which are at a fixed distance from a fixed point. And this fixed point is known as the center of the circle. This fixed point is known as the center of the circle. And this fixed distance from the center to the circle and this fixed distance from the center to the circle is known as the radius of the circle. Is known as the radius of the circle. Now clear? That means the fixed point is the center of the circle and the fixed distance from the center to the point on the circle is its radius. Now you are clear about what is a circle and what is its center and what is its radius. These three things can be explained in a one stretch. That a circle is collection of infinite number of points or a large number of points which are at a fixed distance from a fixed point. And that fixed point is called the center of the circle. And the fixed distance from the center to the circle. Fixed distance from the center to the circle is the radius of the circle. So when we take distance from the center to any point on the circle, then it is same everywhere and is known as the radius of the circle and is known as the radius of the circle. Clear? Okay, that's what called a circle, its radius and its center. Now we have to explain some more terms related to circles. We need to explain some more terms related to circles. So I am considering the same circle. And this is our circle. And this is our circle. You know that all circles have a fixed center point. All circles have a fixed center point, and I am marking the center of the circle as O. Center of the circle as O. And from the center of the circle, the distance between the center to the circle is a fixed distance and is called the radius. I am marking the radius as R. I am marking the radius as R. Now, when two points on a circle are connected and this line passes through the center of the circle, then it is the diameter of the circle. When two points of a circle are joined together and passing through the center of the circle, then this is the diameter of the circle. Then this AB can be called as the diameter. So the points or the line connecting two points on the circle and passing through the center of the circle is the diameter of the circle. And we are having a relation between radius and diameter as 2 into radius is the diameter of the circle. 2 into radius is the diameter of the circle. That means always double the radius gives diameter, or half of the diameter is the radius of the circle, or otherwise we can say that radius R is equal to diameter divided by 2. This is the relation between radius and diameter. Always half of the diameter gives radius, or otherwise we can say that double the radius gives diameter. That's what a diameter is called. Then moving to the next term related to circle, that is a chord. Chord is simply a line connecting any 2 points on the circle. Chord is simply a line connecting any 2 points on the circle. Now look at the line joining C and D. It is 2 points on the circle and CD is the line joining these points. Then the CD can be called as a chord. Then if I am considering another 2 points X and Y, then XY can be called as another chord on the circle. Like in the circle, the line joining any 2 points can be called as a chord. Now look at AB. We all know that AB is the diameter. Also, AB is the line joining 2 points on the circle. Therefore, AB can also be called as a chord. AB can also be called as a chord. Therefore, diameter is also simply a chord. And this is the largest chord in a circle. Now we can say that diameter is the largest chord which can be drawn on a circle. Diameter is the largest chord which can be drawn on a circle. All diameters are chords, but all chords are not diameters. Remember this thing, all diameters are chords, but all chords are not diameters. Clear? Circle, center, radius, diameter and chord. The next term related to circle is arc. Next term related to the circle is arc. So now I am going to explain what do you mean by an arc. A portion of a circle is known as the arc. When I am considering this portion, this is A and this is B, then this AB can be called as an arc. This AB can be called as an arc. This is an arc. That means a portion of the circle is called as an arc. An arc can be classified as minor arc and major arc. That simply means smallest arc is the minor arc and the largest arc is the major arc. Now when you look at this picture, AB, this is the smallest arc. Therefore, this can be called as minor arc. This can be called as minor arc. And now look, I am writing one more point here, C. Now look at ACB. This is the larger arc. Therefore, this can be called as major arc. This can be called as major arc. So, the smallest arc is the minor arc and the largest one is the major arc. That's what about arc. Now, moving to the next, it is segment. It is segment. What do you mean by a segment? Now, consider a small chord here. It is CD. Now, this C and D gives also an arc here. CD is a small arc here. Then the region between this arc and chord is the segment. The region between this arc and chord is the segment. This is a segment. This is a segment. And this segment can also be called as minor or major segment. The smallest segment is the minor segment and the largest one is the major segment. Now look at this figure. This is the smallest portion. Therefore, this is the minor segment. And this is the largest portion or this is the largest segment. Therefore, this is the major segment. This is the major segment. The region between a chord and an arc is the segment. And the smallest segment in the circle is the minor segment and the largest one in the circle is the major segment. That's all about segment. Now the next term we have to explain is sector. What is a sector? Now consider two radius of the circle, that is OC and OD. Consider two radius of the circle OC and OD. Now this is CD is an arc. You know that CD is an arc. This is an arc. and OC and OD are radius of the circle. Now look at this portion. Now look at this portion. OC and OD are radii of the circle and CD is the arc of the circle. Now, when this arc and the radii of the circles are joined, when the end points of a arc are joined to the radii of the circle, then we got a region, and the name of the region is called sector. And the name of the region is called sector. In here, sector also, there is major sector and minor sector. Now look at this figure. This is the smallest region where the radius of the circle and arc are joined. Therefore, this is the minor sector. And what the remaining region? This is the larger one. Therefore, it is called as major sector. It is called as major sector. That's all about sector. Now, the total length of the circle. Now, the total length of the circle is known as the circumference of the circle. Is known as the circumference. Simply, circumference means perimeter of the circle. Simply, circumference means perimeter of the circle. That means the total length of the circle. Total length of the circle. If the circle is made it to a straight line, then what is the length of the line? Then it is the circumference, or simply it is the perimeter of the circle. These are all terms related to circles. Now, when we are marking points, we can classify the point as interior point, exterior point, or point on the circle. If the point is inside the circle, like this, I am marking a point X. Now this point is interior of the circle or inside the circle. If a point is inside the circle, then this point can be called as interior point. Then this point is called as interior point. If I am marking a point like this, Y. This is point on the circle. This is point on the circle. And if I am marking a point outside the circle, then the point is known as exterior point. Then the point is known as exterior point. Then the point is known as exterior point. So when we are marking points, we can mark the points as interior point on the circle and exterior. If the point is inside the circle, it is interior point. And if the point is on the circle, then it is the point we just call it as on the circle. Then if the point is outside, then it is exterior point. Then it is exterior point. Clear? Okay. Now, we explained about the chord and arc and chord joined together to form a segment. Now, when we are considering a diameter, now look at this figure. AB is a diameter, and you know that AB is an arc here. AB is an arc here. When this AB, that means the arc AB and the diameter AB joins, then we got a region like this. This is also a segment. This is also a segment. But the importance of this is that here minor sector and major sector are of same area. Major sector and minor sector are of same area. That means both minor and major sector are same. If both of them are same, then we need not to call it as major or minor. If it is larger and smaller, then we call major and minor. If it is of same area, then we need not to call major or minor. Then we call this as semicircles. That means if the endpoints of a diameter and the arc are joined, we got a region called semicircles. So when we are considering a semicircle, when we are considering a diameter, we got two semicircles here. That's all about the important terms. Related to circles. Now, what is a circle? Now you can explain all these terms. What is a circle? Circle is a collection of large number of points which are at a fixed distance from a fixed point. And that fixed point is the center of the circle. That fixed distance is the radius of the circle. Always double the radius of the circle gives the diameter. That means the line joining two points on a circle and passing through the center of the circle is the diameter. Also, it is the largest chord in the circle. A line joining any two points on the circle is the chord. And a portion of the circle can be called as an arc, and the smallest portion is minor arc and the largest portion is major arc. When a chord and an arc is joined, we get a region, and that region is the segment. When we are considering smaller arc and a chord, then we get minor segment, and the larger one is the major segment. When two radius of the circle and an arc are joined together, we got a region called sector. The smallest sector is the minor sector and the largest one is the major sector. And the total length of the circle, is the circumference of the circle, When a diameter and the arc are joined together, we got a region called a semicircle. When we are considering a diameter, we got two semicircles here. And when we mark points, we can mark interior points, exterior points, and points on the circle. When the point is inside, it is interior point, and when the point is outside the circle, it is exterior point. And points marked on the circumference of the circle is the point on the circle. That's all the terms related to circles. This is the basic thing related to circle. What do you mean by circle or terms related to circles? Now, you are clear about what is a circle and what are the terms related to circles. Now, we can move to the theorems in this chapter. Okay, clear? Now, moving to the theorems related to circles. And this is our first theorem in this chapter, theorem number 1. Take a notebook and write all the theorems related to circles. Now we are going to discuss the first theorem, theorem number 1, which is related to the angle subtended by a chord at the center. Angle subtended by a chord. Angle subtended by a chord at the center of the circle, at the center. The theorem related to fact angle subtended by a chord at the center. Now we can consider a circle. I am going to consider a circle. This is our circle. Now, the theorem angle subtended by a chord at the center. Okay. Now I am considering a chord and named it as AB. Center is O. Now, this is the angle subtended by the chord at the center, that is angle AOB. Okay. You all know that theorems are general statements which can be applied to all problems related to the given fact. Theorems are general statements which can be applied to all problems related to the given fact. So in this case, the angle subtended by the chord at the center, we cannot give an accurate value. Maybe it is 50 degree or 60 degree, 70 degree, 80 degree or 45 degree. We cannot give it as an accurate value, but we can say a general fact related to this condition, or we can give a general statement related to this fact. by using that general statement, we can apply this to the related problems and thus by finding the accurate value. Clear? And now I am going to give the general statement. For that general statement, I consider one more code, that is CD. And this code CD also makes an angle at the center, that is angle COD. Now moving to the theorem. The theorem is that theorem number 1. Just note it in your book. Theorem number 1. First theorem in this chapter, circles. First theorem, that is theorem number 1, states that equal chords subtends equal angles at the center. Equal chords of a circle subtends equal angles at the center. Now suppose if AB is equal to CD, that means if both the chords AB and CD are equal, then angle AOB should be equal to angle COD. That is, if the chords are of equal length, then the angle subtended by this chord, if the chords are of equal length, then the angle subtended by this chord should also be equal. Then the theorem 1 is that angle, theorem 1 is that equal chords of a circle, equal chords of a circle subtends equal angles at the center. This is the theorem. Equal chords of a circle subtends equal angles at the center. Now if AB and CD are equal chords, then this AB and CD will subtend equal angles at the center. That means if AB is equal to CD, then angle AOB is equal to angle COD. This is a general statement and this statement can be used in all problems related to fact angle subtended by a chord at the center. If we are given two equal angles, two equal chords, then these chords surely make equal angles at the center. That is theorem number 1. Just note the theorem. Theorem number 1, equal chords of a circle subtends equal angles at the center. Okay, this is theorem number 1. So theorem number 1, first theorem is completed, and next theorem number 2, second theorem in this chapter. And this theorem is related to the fact a perpendicular drawn from the center to a chord. Perpendicular drawn from the center to a chord. Perpendicular drawn from the center to a chord. For this theorem also, I am taking a circle and this is our circle and I am marking the center as O. Now what is the condition? Perpendicular drawn from the center to a chord. So I have to consider a chord and this is our chord. This is chord AB. And perpendicular drawn from the center to the chord. This is the perpendicular. Take it as OM. OM is the perpendicular and AB is the chord. AB is the chord. OM is the perpendicular. OM is the perpendicular. Now, in theorem 2, there is a general statement. Like in theorem 1, in theorem 2 also, there is a general statement explaining the condition or regarding the condition perpendicular from the center to the chord. Now we can move to the theorem number 2. Write it down in your notebook, theorem number 2. Theorem number 2 states that a perpendicular drawn from the center of a circle to a chord bisects the chord. A perpendicular drawn from the center of a circle to a chord bisects the chord. That means OM is the perpendicular. OM is the perpendicular. This OM bisects the chord AB. OM bisects the chord AB. OM bisects the chord AB means AM is equal to BM. This is the condition. AM is equal to BM. This is the condition. Now theorem 2 can be stated as a perpendicular drawn from the center of a circle, perpendicular drawn from the center of a circle to a chord bisects the chord. To a chord bisects the chord. A perpendicular drawn from the center of a circle to a chord bisects the chord. Here OM is the perpendicular and AB is the chord. So OM is the perpendicular from the center. This perpendicular bisects the chord and AB is the chord. OM bisects the chord, which simply means that the length AM and BM are equal. The length AM and BM are equal. This is theorem number 2. Okay. We can solve problems based on all the theorems after completing all the theorems in this chapter. This is theorem number 2. Okay. Clear? And moving to the next theorem, theorem number 3. Theorem number 3 is related to circles passing through 3 points. Circles passing through 3 points. Based on this fact, we have to state the theorem 3, third theorem in this chapter. Circles passing through 3 points. So, if we are given 3 points like A, B, and C. And what is the peculiarity of these 3 points? These 3 points are non-collinear points. What do you mean by collinear points and non-collinear points? Collinear points are those points which lie on the same line. Collinear points are those points which lie on the same line. Here, A, B, and C. These 3 points are non-collinear because these 3 are not on a same line. These 3 didn't lie on a same line. Not on a same line, therefore can be called as non-collinear points. So A, B, and C are 3 non-collinear points. A, B, and C are 3 non-collinear points. 3 non-collinear points. Now try to draw circles passing through these 3 points. Try to draw circles passing through these 3 points. You also try. Just take a sheet of paper and mark 3 points. Anywhere you like, mark 3 points. and try to draw a circle passing through these 3 points. After completing one circle, try to draw another circle passing through the same 3 points. After completing second, try to draw another one passing through the same 3 points. So try as much as you can and write the number of circles that can be drawn which is passing through these 3 given points. Find the number of circles. If you find the number of circles, then you got the third theorem. Then you got the third theorem, that is theorem number 3. When we try to do this, that means trying to draw circles passing through 3 non-collinear points, we can draw only one circle. We can draw only one circle. That means in general we can say that there is only one circle passing through 3 non-collinear points. There is one and only one circle passing through 3 non-collinear points. So this is theorem number 3. Theorem number 3 is there is one and only one circle. There is one and only one circle. There is one and only one circle passing through 3 non-collinear points. 3 non-collinear points. This is theorem number 3, third theorem. What is theorem number 3? It is related to the fact circles passing through 3 points. When we are considering 3 points which are not on a same line, which are of different positions, that these 3 points are known as non-collinear points. So when we consider A, B and C, this A, B and C are 3 non-collinear points. When we are trying to draw circles exactly passing through these 3 points, we can draw only one circle passing through these 3 non-collinear points. Trying again and again gives only one circle passing through these 3 non-collinear points. That simply means, in general, we can say that there is only one and only one circle. There is one and only one circle passing through 3 non-collinear points. If we are considering 3 non-collinear points, we can draw only one circle passing through these 3 non-collinear points. This is theorem number 3. This is the third theorem in this chapter. Write it down. Okay, clear? 3 theorems are now completed. And now we have to explain the fourth theorem. Fourth theorem is related to the fact equal chords and their distance. Equal chords and their distance from the center. This is the condition for the fourth theorem. Equal chords and their distance from the center. Here also I am considering a circle. And this is our circle. And consider chords. This is AB. And this is CD. And this is XY. These 3 are chords of equal length. Let it be considered of equal length. That means AB, CD and XY are chords of equal length are chords of equal length. AB, CD and XY are chords of equal length. Now, this is the center O. And what is the distance? Equal chords and their distance from the center. That is what in our condition. So, take the distance from the center to the chord CD as X. And the distance from the center to the chord AB as Y. And the distance from the center to the chord XY as Z. Then what is in general regarding these distances from the center to these chords? What is the distances X, Y and Z? The peculiarity of the chords given here is that this AB, CD and XY are chords of equal length. Chords of equal length are always equidistant from the center. Chords of equal length are always equidistant from the center. That means the distance from the center to the chords of equal length are equal. That simply means that here x equal to y equal to z. Here x equal to y equal to z. That means x equal to y equal to z. O is the center. A, B, C, D and X, Y are the chords of equal length. So from the center to these chords, distance are equal because chords are of equal length. Now, next theorem is theorem number 4. So theorem number 4 states that chords of equal length are equidistant from the center. Chords of equal length are equidistant from the center. Here A, B, C, D and X, Y are chords of equal length. Therefore, the distances of these chords from the center are also equal. This is theorem number 4. Chords of equal length are equidistant from the center. Chords of equal length are equidistant from the center. This is theorem number 4. We completed 4 theorems in this chapter, 1, 2, 3 and 4. Now moving to the next theorem related to a topic, angle formed in a segment or angle subtended by a chord in a segment. Related to this fact, we are having 3 theorems, 5, 6 and 7. And these 3 theorems are related to the fact angles in a segment, related to the condition or related to the fact or related to the theory, angles in a segment. And the first theorem related to that is the angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining parts of the circle. For this theorem, I am considering a circle. Consider this as a circle, and what the theorem says, the angle subtended by an arc at the center. Now consider an arc. This is AB and this is center O, and this is the angle AOB. This angle is double the angle subtended by it at any point on the remaining part of the circle. It is the double the angle subtended by it at any point on the remaining parts of the circle. So I am considering another angle, angle ACB. The theorem says that angle AOB is double the angle of angle ACB. That simply we can say that angle AOB is equal to 2 into angle ACB. Angle AOB is equal to 2 into angle ACB. This is what in theorem number 5, the angle subtended by an arc at the center. Any angle subtended by an arc at the center is double the angle subtended by it by the same chord at any point on the remaining parts of the circle other than the center, at any point on the remaining parts of the circle. So here AB is our chord and this AB makes an angle, suppose let it be X, makes an angle X at the center, and the same chord AB makes an angle, let it be Y, at any other point on the circle. Then we can say that X is equal to 2Y or Y is equal to X by 2 or Y is equal to X by 2. This is the condition that's set in the theorem number 5. The angle subtended by a chord at the center of the circle is double the angle subtended by it at any point on the remaining part of the circle. At any point on the remaining part of the circle. This is theorem number 5. Now theorem number 6 says that, theorem number 6 says that angles in the same segment of a circle are equal. Angles in the same segment of a circle are equal. Again, considering a circle, and consider a segment. This is a chord AB and consider this segment. This is the segment formed by major arc AB and the chord AB. Major arc AB and the chord AB forms here the major segment. And what the theorem says, angles in the same segment of a circle. That means from this chord here an angle is formed. That is angle ACB. Let it be X. And I am considering another angle which is angle ADB. Let it be Y. Also I am considering one more angle. Let it be AEB. Angle AEB. Let it be Z. Now in this theorem, it is saying that angles in the same segment of a circle are equal. That means this angle X, Y and Z are lying on the same segment, Therefore, these three angles are equal. That is X equal to Y is equal to Z. That is X equal to Y equal to Z. Clear? Angles in the same segment of a circle. These angles X, Y and Z lies on the same segment. Therefore, these angles are equal. That's what in the theorem number 6. Angles in the same segment of a circle are equal. Moving to the 7th theorem. Next theorem related to angles and segment. What is it? If a line segment joining 2 points, and subtends equal angles at 2 other points lying on the same side. Subtends equal angles at 2 other points lying on the same line. Containing same line segment, then 4 points lie on a circle. That simply means if a line segment joining 2 points, I am considering a line segment A, B and joining the points A and B, subtends equal angles at two other points lying on the same side. Subtends equal angles at two other points lying on the same side, that is x, y. Sorry, both are equal angles, therefore both can be taken as x. Then these 4 points lie on a circle. Now look, A, B, C and D are on a same circle, which is related to the sixth theorem also. We know that angles in the same segment are equal. So when we consider 2 points connecting a line segment which is A and B, that can be called as a chord of a circle. Then if these 2 points and these 2 points connecting the line segment, which may be a chord, makes equal angles at 2 other points, then simply it means that they are forming angles on the same segment. Then we know that these 4 points lie on a circle. Then these 4 points lie on a circle. This is theorem number 7. So theorem 6 says that the angle formed by a chord at the center is double than the angle formed at any other points on the circle. And the sixth theorem is angles in the same segment of a circle are equal. And the seventh one is when we consider a line segment joining 2 points, and if these 2 points subtends equal angles at 2 other points lying on the same side, then these 4 points lie on a circle. These are the theorems 5, 6 and 7 related to segments and angles. Okay. Now moving to the last theorem of this chapter relating to the topic cyclic quadrilaterals. Cyclic quadrilaterals. And related to the cyclic quadrilateral, we have the last theorem, theorem number 8. Theorem number 8. So basically we need to know what is a cyclic quadrilateral. Then we can move to the theorem. Now look at this quadrilateral ABCD. What is the peculiarity of this quadrilateral? All the 4 vertices are on the circle. All the 4 vertices are on the circle. That means a quadrilateral is cyclic if all the 4 vertices are on a circle. So ABCD is a cyclic quadrilateral because all the 4 vertices A, B, C and D lie on a circle. So what do you mean by a cyclic quadrilateral? If all the 4 vertices of a quadrilateral are on a circle, then the quadrilateral is cyclic. If all the 4 vertices, if all the 4 vertices of a quadrilateral lies on a circle, if all the 4 vertices of a quadrilateral lies on a circle, then the quadrilateral is cyclic. Then the quadrilateral is cyclic. If all the 4 vertices of a quadrilateral lies on a circle, if all the 4 vertices of a quadrilateral lies on a circle, then the quadrilateral is cyclic. Here ABCD is cyclic. ABCD is a cyclic quadrilateral. Related to the cyclic quadrilateral, we have a theorem that in a cyclic quadrilateral, either the pair of one of the opposite angles the sum of that angles is 180 degree. That means if we are considering angle B and angle D, then angle B plus angle D is equal to 180 degree. In a cyclic quadrilateral, the sum of either pair of opposite angles is 180 degree. In a cyclic quadrilateral, in a cyclic quadrilateral, the sum of either pair of in a cyclic quadrilateral, the sum of either pair of opposite angles is 180 degree. Is 180 degree. That means the sum of opposite angles is supplementary. The sum is 180 degree. Therefore, opposite angles can be called as supplementary. So, in a cyclic quadrilateral, either pair of opposite angles is supplementary. Simply, we can say that either pair of opposite angles is supplementary. Otherwise, we can say that sum of either pair of opposite angles is 180 degree. So, what is a cyclic quadrilateral? The quadrilateral in which all the four vertices are on a circle. This is a cyclic quadrilateral. What is the theorem related to cyclic quadrilateral? In a cyclic quadrilateral, the sum of either pair of opposite angles is 180 degree. That means either pair of opposite angles are supplementary. Clear? Okay. All the theorems related to 9th grade circles are now completed. Then we can solve some problems based on that theorems we have studied earlier. Okay. We already studied 8 theorems from this chapter and just memorize these 8 theorems or write it in a notebook, theorem 1, 2, 3, 4, etc. up to 8, and just memorize all these theorems. And using these 8 theorems, we can solve all the problems in this chapter. And you are having to exercise in this chapter for some problems related to these theorems. And I am solving some of the problems, and you have to solve more and more problems based on this theorem. Okay. The first problem is two circles of radii 5 centimeter and 3 centimeter intersect at 2 points, and the distance between their centers is 4 centimeter. Find the length of the common chord. So we are having two circles of radii 5 centimeter and 3 centimeter. So first of all, I have to draw two circles of radii 3 centimeter and 5 centimeter. First, I am drawing a circle of radii 3 centimeter, which is the smallest circle. This is our smallest circle. This is a circle of radius 3 centimeter. Fine. Now we have to draw a larger circle. Now we have to draw a larger circle. And this is our larger circle. And These two circles intersect at 2 points. Which are the points? This is point. And I am taking it as A. And this is the next point. I am taking it as B. And this is the common chord. AB is the common chord. And marking the centers. This is the centers of both circle, and the distance between them is given as 4 centimeter. And this is the radii of small circle. It is given as 3 centimeter. And this is the radii of larger circle. It is given as 5 centimeter. Now we want to calculate the length of AB. Just take it as O, and this is M. So we want to calculate the length of the common chord, that is AB. Length of the common chord, that is AB. How to find this? So now AOM is a triangle. We know that AOM is a triangle. We have to check whether it is a right angled triangle or not. We have to check whether this is a right triangle or not. If it is a right triangle, then here the angle becomes 90 degree. Then here the angle becomes 90 degree. If the angle is 90 degree, then by theorem we can say that perpendicular drawn from the center to the chord bisects the chord. If it is 90 degree, we have to check whether it is 90 degree or not. If it is 90 degree, then we can say that a perpendicular drawn from the center to a chord bisects the chord. To a chord bisects the chord. So first of all, we have to check whether it is 90 degree or not. How we can check? We know all the three sides of the triangle. This is 4 centimeter, this is 5 centimeter, and this is 3 centimeter. If all the three sides are known, then by applying Pythagoras theorem, we can check whether it is right angled or not. If Pythagoras theorem is satisfied with these three values, with these three sides, then this is a right angled triangle. If the Pythagoras theorem is not satisfied, then this is not a right angled triangle. So I am going to apply Pythagoras theorem in this triangle, that is hypotenuse square is equal to base square plus altitude square. Which is the hypotenuse here? AO is the hypotenuse. Therefore, AO square is equal to, which is the base, OM square plus altitude AM square. So AO is 5. 5 square is equal to OM is 4 square plus AM is 3. Therefore, 3 square. 5 square is 25 is equal to 4 square 16 plus 3 square 9. That is 25 is equal to 16 plus 9, 25. Left hand side is equal to right hand side. That is 25 is equal to 25. That means Pythagoras theorem is satisfied here. Pythagoras theorem is satisfied here. If Pythagoras theorem is satisfied, then we can say that triangle AOM is a right angled triangle. Triangle AOM is a right angled triangle. Now we can say that triangle AOM is a right angled triangle. Triangle AOM is a right angled triangle. Triangle AOM is a right angled triangle. So this is 90 degree. Now by theorem, we can say that this perpendicular bisects the chord. O is the center of the larger circle, and we have now angle OMA is equal to 90 degree. Therefore, OM is the perpendicular. If a perpendicular drawn from the center of a circle, then it bisects the chord. That's the theorem. So, by theorem, we can say that OM bisects AB. OM bisects AB, which is AM is equal to BM. From this, we got the condition AM is equal to BM. We know that AM is equal to 3 centimeter. Therefore, BM is also 3 centimeter. So, AB is equal to AM plus BM. That is equal to 3 plus 3, which is 6 centimeter. We know that. Here we know that OM bisects AB. OM bisects AB means AM is equal to BM. AM, it is given that 3 centimeter. Therefore, BM is also 3 centimeter. For finding the common chord, length of common chord AB, which is AM plus BM, that is 3 plus 3, it is 6 centimeter. AB is equal to 6 centimeter. AB is equal to 6 centimeter. This is the length of the common chord. Okay, clear? Then moving to the next question. If a line intersects two concentric circles, what do you mean by concentric circles? Circles having same center. Concentric circles means circles having same center. With a center O at A, B, C and D. A line intersects two circles at A, B, C and D. Figure is given. We want to prove AB is equal to CD. We want to prove AB is equal to CD. Now, O is the center of both the circles. O is the center of both the circles. Now, what I am going to do is, I am drawing a perpendicular from O to the line segment and mark it as M. That is, OM is the perpendicular. OM is the perpendicular. Now, by theorem, you all know that a perpendicular drawn from the center bisects the chord. So, for the larger circle, AD is the chord and OM is the perpendicular. Then OM bisects AB. AD. For the larger circle, we can say that OM bisects AD. This is by theorem. OM is the perpendicular and AD is the bisector. Oh, sorry, AD is the chord of the larger circle. Then OM bisects AB. That is AM is equal to DM. And for the smaller circle, the same OM bisects BC because BC is the chord of the smaller circle and OM is the perpendicular. Therefore, OM bisects BC. That is BM is equal to CM. Now, we can write AM as, look at this figure, AM can be written as BM plus AB, or otherwise we have to prove AB. Therefore, AB can be written as AM minus BM. And in the same way, CD can be written as DM minus CM. Okay, which is equal to, now we know that AM and DM are equal. BM and CM are equal. So, if AM is equal to DM is equal to X and BM is equal to CM is equal to Y, then AM minus BM is equal to X minus Y and DM minus CM is equal to X minus Y. That simply implies AB is equal to CD. That simply implies AB is equal to CD. That's what we have to prove in the question. AB is equal to CD. Clear? If AB and CD, we have to prove AB and CD are equal. So, first of all, we know that AM is equal to DM and BM is equal to CM. So, AB is AM minus BM and CD is DM minus CM. If both these are same, then AB is equal to CD. Clear? Okay. Now, look at this next question, which is the third question. A, B, C are 3 points on a circle with center O. Look at this figure. A, B, C are 3 points on a circle with center O, such that angle BOC is equal to 30 degree and angle AOB is equal to 60 degree. If D is a point on the circle other than the arc ABC, find angle ADC. How to find angle ADC? Simply we can find when I am drawing a chord from A to C, then AC is a chord and angle AOC is the angle formed by the chord at the center. That is, angle AOC is equal to the angle formed by the chord at the center. What is angle AOC? Angle AOB is 60 degree and BOC is 30 degree. Then what is angle AOC? It is 60 degree plus 30 degree, that is 90 degree. That is 90 degree. Angle AOC is equal to 90 degree. Then by theorem we all know that the angle subtended by a chord at the center is double the angle than the angle formed at any other parts. That means angle AOC is double the angle of ADC. That is simply means that angle ADC is equal to half of angle AOC. Half of angle AOC. Angle AOC is 90 degree. Therefore, half of angle AOC is 45 degree. That is angle ADC is 45 degree. Angle ADC is 45 degree. Clear? Next question is, a chord of a circle is equal to the radius of the circle. In a circle, so basically we have to consider a circle. This is the circle. And a chord of a circle is equal to the radius of the circle. Find the angle subtended by the chord at any point on the minor arc and also a point on the major arc. So we have to find the angle subtended by the chord on the minor arc and the major arc. Now I am considering a chord. This is our chord. And I am taking the radius as OA and OB. Now in the question it is given that the chord is of same length of radius. So OA is equal to OB is the radius of the circle, which is same as length of the chord, which is given in the question. So all these three sides of the triangle are equal. Then this triangle is an equilateral triangle. Then this triangle is an equilateral triangle. For an equilateral triangle, all the angles are equal. That is, all these angles are 60 degree each. All these angles are 60 degree each. So when we consider an angle formed in the major segment or the major arc, when we consider an angle formed in the major arc, it is half the central angle formed. That is, central angle is 60 degree, therefore it is 30 degree. When we consider an angle on the minor arc, how to find the angle formed on the minor arc? The angle formed on the major arc and angle formed on the minor arc are supplementary. That means when we add these, we get 180 degree. How? When we consider this ABCD, then look ACBD. This is an cyclic quadrilateral. This is a cyclic quadrilateral. All the four sides lie on a circle. Then we can say that by theorem, for a cyclic quadrilateral, either pair of opposite angles are supplementary. So angle C and angle D are opposite angles. These should be supplementary. That is, sum is 180 degree. Therefore, we can say that angle D is equal to 180 minus 30 degree, that is 150 degree. That is 150 degree. This is 150 degree. So angle formed on the major arc is 30 degree and angle formed on the minor arc is 150 degree. That's all about this chapter. chapter number 10, circles. You just go through all the theorems, 1, 2, 3, 4, etc. up to 8. We already discussed about 8 theorems. Just memorize all these 8 theorems and then solve problem like this. Then it will be easy for you. I think all are clear to you. And I am Nitishas. Thank you for joining me in this section. Let us meet with another chapter or another section in another class.